Okay, let's go ahead and get started on some examples of trig derivatives. But before we do, for those that kind of skipped over the last one, finding out that I was merely deriving and sort of justifying our use of the derivatives, let's go ahead and go over once more, since repetition is pedagogically advantageous. How many times have you heard me say that? Okay. And I told you at the end of the last video that you don't actually have to memorize all of them, okay? Now this first one right here, that ought to be the easiest one. You've seen it 1,000 times already. It ought to be instinctive right now that the derivative of sine is cosine, okay? And now that means that all you really have to do is memorize these two. And all you have to do to confirm that is just look at the way I've arranged them. I've arranged sine, tangent, and secant next to their corresponding cofunctions, right? And cofunctions are, of course, come from the relationship of sine and cosine, function and cofunction, and their complementary angles. So like I said in the last video, sine of 30 degrees is equal to cosine of 60 degrees. Tangent of 30 degrees is equal to cotangent of 60 degrees. Secant of 30 degrees is equal to cosecant of 60 degrees, and other combinations of complementary angles. Okay, and what's great about trig that we hinted at, or not hinted at, but actually got a first dose of last year, is the fact that because they're all anchored in this relationship within a right triangle, they all have necessary relationships to each other. And we see that borne out even here in their derivatives. So the sine of a function, the derivative of a function is, whatever it is. The derivative of its cofunction is equal to the negative cofunction of the original derivative. So notice that sine and cosine are cofunctions, right? Negative sine and cosine are negative cofunctions. Tangent and cotangent are cofunctions. Cosecant squared and negative cosecant squared, this one's negative, and all the functions here are the cofunctions of the ones over here. Now granted, you have two of them, right? It's secant times secant, and here it's cosecant times cosecant. But still, the pattern holds. This is a negative, and it's the cofunction of the original derivative. Down here again, you get secant tangent, cosecant cotangent, with a negative plopped out in front. So if you remember this one and the pattern, the only two that actually need to be memorized are these two right here. So I won't belabor that point anymore. We'll go ahead and get started with some examples. Let's go ahead and start off with a relatively straightforward one, sine x times cosine x. Now, from here, we obviously have a combination function. It's not only trig, it's combo. The combination is a product. It's a product function, and therefore we need to use the product rule. Okay, so remember that it doesn't really matter which one you do first. So let's go ahead, just because I know what this is going to be. I'm going to do it in the opposite order that I usually do it in. I'm going to say second times the derivative of the first plus the first times the derivative of the second. And remember, because multiplication and addition are commutative, I can go ahead and do that. Now the reason that I did that is the moment I get cosine squared minus sine squared x, that ought to look eerily familiar. And if it doesn't, it's because you're not keeping up with your trig IDs. You have to keep up with your trig IDs. Those are going to be incredibly important as you move forward. Those are not just for last year. There's a reason that they called the class before this pre-calculus. As in, the last few things that you need before moving into calculus. Need before you move into calculus. Now, you don't really need it here. It does wind up being very, very helpful, the fact that this is cosine of 2x. Well, could I have foreseen that? Well, if we look ahead and sort of hint about where we're going, You remember that sine x times cosine x is not an identity, but it's awfully close. So if I multiply it by 1/2 and 2, because I can do that, if I multiply by 1/2 and 2, I've really multiplied by 1. This right here is an identity. That is the double angle identity for sine. And we can see, even if we don't fully remember everything that's involved with the chain rule, you can see the relationship between these. Okay? Now, so I can do it, once I get to the chain rule, I can do it by changing the form using trig ID, or I could have, of course, just done it by the product rule. It doesn't really matter. Now, why do I mention that if we haven't gotten to the chain rule yet? That is a fantastic question. The reason that I mention it now is because I'm trying to continually remind you that before you ever start a problem, before you start grinding away on a method or a procedure, you need to stop, think, then do. Especially with the trig ones, because the change of form winds up being so pivotal on some of them in terms of turning a monstrous question, just a function that just looks as nasty as can be, into something that actually isn't really all that bad. Okay? Now, let's go ahead and look at the next one. You have sine of t times secant squared t. Well, if you remember the chain rule, you see the fact that that involves the chain rule inside of the product rule. But let's say that I don't want to deal with the chain rule just yet, okay? And the reason that this looks like chain rule is because this problem is taken from a book that introduces the chain rule before trig derivatives, whereas your book does it in the opposite order. But here's the thing, we can use a change of form here as well. Why don't I let the sine borrow one of those secants? Because once you multiply sine times secant, you're really dividing sine by cosine, and that winds up being tangent t times secant t, and that right there is actually a pretty easy product rule question. So we'll go ahead and say the first, which is tangent t, times the derivative of the second, and that's secant t tangent t, plus the derivative of the first, and that's the derivative of tangent, which is of course secant squared, times secant t times the second, right? Well, I don't really have to do it, but I can go ahead and pull out a secant t if I want, and that makes tangent squared t plus secant squared t, and that's not an identity, but you could probably change the form a little bit more and get it closer to what you want it to be. You could probably go ahead, you could do it in terms of a denominator, because both of these terms have cosine cubed in the denominator. So you have that going for you. But remember, like I said, simplifying and changing the form after you actually do the calculus, it becomes a little bit more vague when you get to calculus, because what form you change it into has everything to do with what you're going to do with it next. And if you don't know what you're going to do with it next, then you really just are good just go ahead and leaving it, do rudimentary simplification. Cancel, terms that are additive inverses. Cancel factors. Combine like terms. Reduce fractions and stuff like that. But I wouldn't go overboard in terms of doing any simplification unless your teacher requires you to. Because really a lot of it is just unnecessary jumping through hoops. Because if somebody says, well, are you going to simplify that? The answer back should be, well, into what form? What am I going to do with it next? What do I need this derivative for? Okay, so let's go ahead and jump ahead to another problem. That's 1 plus tangent x over 1 minus tangent x. Now, this is obviously a quotient rule problem. You could change the form. There's really no need to change the form right here. There's really going to be no advantage to it. At least not that I can see on the face of it. It's a little bit nasty, not because the concept is difficult, but because anytime you introduce more terms and more factors, and especially when you introduce a quotient, it's just a matter of it becomes cumbersome in terms of keeping everything in order. But as long as you use your parentheses and your brackets and you're careful, it really shouldn't be that big of a deal. So let's go ahead and do it by the quotient rule. I know that I'm going to need the top, 1 minus tangent x. That's how I start. Okay, no parenthesis, not bracket. I haven't taken a derivative yet. And this is one of those places that is actually really useful to use that sort of notation that I use, where the brackets indicate where I indeed have taken it. Now, 1 minus tangent x, the derivative of 1 is obviously 0. The derivative of negative tangent is obviously negative secant squared. And then I'm going to subtract the top, 1 plus tangent x, and then, of course, we get secant squared x as the derivative there. All of that over 1 minus tangent x squared. Okay, well, I can go ahead and simplify this a little bit. I'm going to get negative secant squared x plus secant squared x tangent x minus secant squared x. Now remember, that negative is because you're having to distribute the secant squared, but you're also having to distribute the negative across here. So I mean, you could actually turn that into a plus and just sort of put the negative over here with the secant squared, so you don't have to look in two different directions to do the distribution. It's up to you, though. Minus secant squared tangent x, sorry, there's supposed to be an x right there, all of that over 1 minus tangent x squared. Now we see the fact that there's a little bit of cancellation that can be done here, and it winds up being negative 2 secant squared x over 1 minus tangent x squared. And that's, you know, it was a little bit messy, but it wasn't too heinous. Let's go ahead and do, I think we're going to go ahead and do an equation of a tangent line, okay? Oh, let's say we're given, oh, and this is a really good one to use. I actually mentioned this one to those of you who were on the BC Skype session, because I went a little bit further with the BC kids, because they're going to start picking up the pace here in the next week. And this is an equation of a tangent line, and it's at t is equal to pi over 3. Now, first things first, I know I need two things for a tangent line. I need point and I need slope, because that's what I need to get the equation of any line, point and slope, right? Well, I don't have point, but point's easy enough to get. I mean, all you have to do is just evaluate y at that, and you get sine of pi over 3 over 1 plus cosine of pi over 3. What's sine of pi over 3? Anybody? Anybody? Yeah, it's because you don't know your unit circle values. Okay, sine of pi over 3 is root 3 over 2, and this is 1 plus, and of course cosine of pi over 3 is going to be the other one, right? It's going to be 1/2, and therefore this is root 3 over 2 over 3 over